This, we are still in notes 5. We are discussing the LAN. So we were looking at, in the last lecture, we were looking at Ethernet. And towards the end, we were looking at the different types like hubs, okay, bus LAN, hub LAN, and switch LAN. Okay. Today, we start with what is called extended LAN. Okay. And specifically, we look at the switches and bridges, which are used to connect one or more LANs to become a single extended LAN. Okay. So now the question is, I mean, if you look at the past history, okay, so usually there is one single network, hub-based or bus-based, okay, so where multiple systems are connected to it. And there was a need to have more than one network, layer 2 network, okay, maybe it could be in different floors or different buildings or departments. So how we can connect multiple LANs together. Okay? So for example, look at this here. So we use a device called bridge, okay, to connect two local area networks. This is, let's say, LAN local area network 1. This is local area network 2. Okay? This bridge is nothing but switch. Of course, there are differences between bridges and switches. So let's not go deep into the differences of bridges and switches, because in maybe 80s, 90s and all, the bridges were developed to connect multiple LANs. Okay? So bridge is used to connect two devices, two local area networks, but later switch evolved, okay, with more maybe ports or more capabilities. Okay, so they also do the same job of connecting multiple LANs. Okay, so whatever we discuss here with reference to bridges or switches, okay, so they refer to both. You can interchangeably use it, bridge or switch. But note that if you Google it or do search in the resource web, so you can find the micro level differences between what is a bridge, what is a switch. Maybe bridge may have limited number of ports, okay, and what type of networks they can support, etc. Okay? But at the network level, we are going to look at later what is called spanning tree protocol and other things, okay, how a tree is formed on the network, okay, or extended LAN. So there, I mean, whether it's a bridge or switch, so the protocol is the same. Okay? So if you look at the books, textbooks, several places they are also using bridges. So I just don't want to avoid the term bridge altogether, because when you read the book, you may see the term bridge. Right? So that's why you can see that I put bridges, switches, slash. So I say they are similar, they are not same, but we use them interchangeably. Okay? And usually when we say two networks, two local area networks, we can use a router to connect both of them. Or we can use switches, for example, Ethernet switches to connect two LANs. So there are two ways to do that. But if you use, let's say this is LAN 1 and this is LAN 2. So let's say use a switch. If it's a switch, okay, the data will go through only layer 2. This is layer 2. If you use a router, data from one LAN will flow all the way to layer 3, then come back. That means we need to do processing based on the layer 3 address, IP address. Okay? But both serve the purpose. Routers are more expensive than switches. So usually switches are preferred in the local environment. There are two types of bridges developed. One, source routing bridge. The other one is transparent bridge or spanning tree bridge. So as I have been mentioning earlier, there were two groups, Ethernet group and token ring group, if you remember, right? So Ethernet was developed or promoted by Xerox Digital Corporations, etc. Token ring was promoted by IBM. Okay? And so both were working on how we can put together multiple local area networks together to form a single extended local area network. Right? The source routing bridge was developed by the 802.5, that's the token ring group. As the name says, in source routing, the source host, whoever is the sender, that has to, okay, in addition to specifying the destination address, it also has to tell the entire path, okay, how the destination can be reached. See, for example, Look at this case. Let's say A wants to send a frame to X. When you say source routing, at the source, we need to specify, okay, as part of the frame, that it should go through bridge. It should go through a bridge to reach X. Is that okay? And if you have more complex connectivity, something like this, so if you look at this, so these blue colored ones are LANs. The single vertical line is just, we denote the LAN as a single horizontal vertical line. Here we use blue color to highlight it. So it's a very complex one. So you can see many switches or bridges. There are 7 bridges or switches to connect multiple local area networks. Is that okay? So in that case, if let's say host, let's say from here, let's say host 1, it wants to send it to host 2, which is attached to another local area network. Then in the case of source routing, this frame should give sufficient information, okay, that something like it should go through B1, let's say B7 to reach H2, or B1, B5, H2. Some information should be there. That means the host should know that the destination will be reached through switches, 1 or 2 multiple switches, one or more switches or bridges. That knowledge it should have. Okay? But what ideally we would expect is that whether a host is directly, host and the destination are directly connected within a single LAN or in an extended LAN, if they are part of 2 different LANs connected with the switches, we want the same treatment. That means the source host will specify the destination host hardware address, MAC address, that's all. What we want is the host 1, the sender, does not need to have knowledge about the presence of the bridges or switches in the network. You go and connect your system to a LAN, okay, there may be the destination host connected to another switch. Your host doesn't want to know that this should go through this switch, this switch, this switch to reach the other one. Is that okay? That's what we want. Note that we are not using routers. We are using just the switches, right? If they are connected to routers, let's say H1 is connected to another router, H1 is connected to another router, then they form, then, okay, the routing would be based on the IP addresses, right? And ARP and other things would be there, this which we discussed in lecture 2. So the other type, okay, promoted by 802.3 group, that means the Ethernet group, basically transparent bridge or spanning tree bridge. Later you'll understand why we call it a spanning tree bridge. So in this case, the host do not or need not have the knowledge of the presence of switches or bridges. Okay, so we don't need to have any extra knowledge. Just go and connect it. Okay. Now, what is a switch or bridge? So you can imagine a simple switch as a box, okay, with multiple ports, where, okay, different switches or other switches can be connected, right? And as I was mentioning earlier, the hosts do not operate in promiscuous mode, but the switch operates in promiscuous mode. That means it receives all the frames, okay, and it receives all the frames and accept all the frames, look into the destination address to make a decision. Okay? But if you look at your computer, the adapter inside this will accept only those frames which are meant for you. Other frames will not be accepted. Even though you receive it, it won't be accepted or copied for further processing. Now, look at this example, the extended LAN with a bridge or switch. Okay? So in this case, the switch is a store and forward switch. Store and forward switch. Let's say A wants to send a frame to X. So A prepares a frame where the destination address will say X. So this is the destination address, right? So when this frame is received by the switch or bridge, the switch has to do some action. Switch is intelligent. Intelligent means it examines the header, it takes some action, okay? When it looks into this, it knows the destination address X, and it should somehow know that X can be reached through port number 2. X can be reached through port number 2. So note that there can be other ports also. Let's say there can be port number 3. There can be another LAN here I just show only 2 lines. Okay. So how the switch knows that the frame can be forwarded through port number 2 or X can be located at port number 2, that is based on the forwarding table, which it has already built or which it will be building dynamically. Okay? So this is the forwarding table the bridge or switch maintains, which has 2 columns, host and the port. And what it says is A, B, C are located on the side of port number 1, A, B, C, 1. Similarly, X, Y, Z can be reached through port number 2. So that information is available in the local forwarding table. Okay? So when it receives a frame whose destination address is X, so the bridge or switch consults the local forwarding table, then it decides, okay, X is on, this is port 2. So send it through port 2. Okay? Now the next question is whether the table is static or dynamic. It should be dynamic in the sense that, for example, X may be connected here, but after some time, this system X may be removed from here, may be connected here, right? Or there could be another port. As I said, this X can be connected to another port, right? So we cannot say that, okay, don't remove your computer, connect to another port. We cannot say that. So similarly, something can be switched off, become faulty, etc., etc. So usually the table entries will be updated dynamically. It will be refreshed dynamically. Now the next question is how the bridge or switch has built this table. Okay, first we assume that this table is available, correct? So how it is built? Because this should be updated dynamically also. See, for example, now XYZ, suddenly a new host W may join here, may be connected here, correct? So it should know that it should enter, it should make another entry, W, port number 2, right? So if the particular host is removed, then it also should know that, okay, this host is not attached to port number 2 or port number 1, right? So now we are going to look at how it learns the locations of different hosts, meaning that how it learns the ports through which frames need to be forwarded to reach that particular destination host. So how it's going to build the forwarding table entries. So this is done by what is called backward learning method. So that sense, they are called learning bridges. So now they are going to learn the forwarding table entries. They are going to learn ABC are located on this side, okay? X, Y, Z are on this side, right? So how it's going to learn, right? Very simple. Let's say somebody from here, let's say we have 3 rows, row 1, 2, 3, right? So somebody here wants to pass a message to somebody on the other side, okay? So Prof, can you pass it to another one, okay? Maybe time we are not allowed to move, so you want to pass maybe some calculator or something to your friend, right? Okay, so you give it to me. So once you give it to me, I understand, I learned that you are in row number 2. You are in row number 2, right? Then I'll know, okay, maybe you may tell the name, okay? So this is whom I want to pass this calculator, right? So I may ask, okay, so-and-so, okay, where are you sitting? So maybe you may raise hand from this side, right? So if I know that he is in row number 3, I'll directly go and pass it, right? If I do not know, okay, where the other person is located, then I will try to know, okay, maybe probe everywhere, okay? So anybody with this name sitting here, this row, or this row, or this row, correct? So what I'm trying to say is, in this case, I may not learn where the destination, whom the receiver is located, but because this student has passed the calculator to me, he is the source, sender, right? I'm sure 100% that he is located in row number 2, right? Similarly, if the bridge or switch receives a frame from A, whatever be the destination, okay? When it receives a frame, the bridge knows that this frame is received from this port. I am receiving a frame from this side, port number 1, okay? And the switch looks into that. The source address is A. So source address is A. So then it learns that host A is located on this side, because it's receiving a frame whose sender or source address is A from this side, right? So slowly it will learn. Whenever it receives a frame, it will learn based on the source address. That's why it's called backward learning. Okay? Initially, the forwarding table is entry. Maybe we take an example to see how the forwarding table is built up. Let's say first there's a frame received, AB. So the notation which I follow here is A is the source, B is the destination address. Because every frame carries destination address and source address. Of course, in the frame, destination address appears first before the source address. Okay? But the notation here, when I say AB, just do not want to confuse. A is the sender, B is the receiver. By the way, do you know why destination address is specified first in the frame, then source? If you look at the frame format, first destination address will be there, then source address. Okay? Similarly, if you look at CRC, I think this we discussed. CRC will be at the end, not as part of the header. Right? That part we already discussed, because we need to carry out the division. Okay? We need to see, the adapter has to see all the bits. Only then it knows the CRC. So it is attached at the end. Right? But within the header, usually destination is first, then the source address. But here in the notation, when I say AB, A is the source, B is the destination. So when such a frame is received at the bridge, now the bridge learns that A is on port number 1. So first, it will make an entry, A1, this entry. So this is host, this is port. Okay? But it does not know where B is. So our assumption is initially the table is empty. Okay, that is practical, right? Initially when it's booted up, the table is empty. So it does not know where B is. So what it will do is it will do broadcast actually. It will send the frame to all the ports except the port from where it received, because there's no point in sending through the same port, 1, right? Suppose you have port 3, port 4, then it will send it to port number 2, port number 3, and port number 4. And at the same time, it has made an entry for A. So B should be there somewhere, port 2, port 3, or port 4. Okay, so wherever it is, it will grab it. Right? But there's no entry for B now. It doesn't know where X is. Where B is. Okay. Now, it receives, let's say, Y comma A. So Y comma A is received from this side, port number 2. So once it looks into the source address is Y. The frame is received with port number 2, so it makes an entry, Y2. Right? But the destination is A, so first it has to look up the forwarding table. Yes, there's an entry for A. It has already learnt A. It is on port number 1, so it will forward it to port number 1. It will not forward it to port number 3 or 4, because it knows that A is on the side of port number 1. Is that okay? Now, let's say it receives BZ. So BZ will be received from port number 1 from this side. So it will learn B port number 1. B is located on port number 1. But Z, it does not know, because there's no entry for Z now. So it will send Z through all the remaining ports. It's a kind of broadcast, because it doesn't know where Z is. Okay. Now it receives C comma B. So it learns C is located on 1, because when it receives this frame, it receives from port number 1, this side. Right? So it will make an entry. Now the destination is B. It already has an entry for B. So B is located on port number 1. Right? it received a frame from port number 1. The destination is also on the side of port number 1. Okay, so it will not do anything. It will not forward it. It will not forward it. So there's no point in sending it again through port number 1. The frame is received from port number 1. Okay, so it somehow will reach port number B because, host number B, because C and B are on the same side. So it doesn't need to forward it. Any doubt? Students, any doubt? Yes? Yes. The refreshment is periodically. Okay, and whenever a new frame is received, right? So there could be two cases. One is when you attach B to another port, if B sends a new frame, so from there it knows that now I'm receiving the frame from B from this port number 2. So it will update it, port number 2, okay? Or if the timer has reached, let's say for every seconds or few seconds, let's say it's refreshing. Refreshing means it will empty the forwarding table again, it will start learning it. Okay? But in between, yes, there's a possibility that it may be misrouted or forwarded. That could happen. Right? Yes. Yeah, so in this case, if it's a broadcast LAN, of course, C would have already received the frame, right? So even if it is broadcast, if it's another switch LAN, okay, there will be a path from there it will reach. It doesn't need to forward it again. So with this, okay, this is a very simple connectivity. One switch, just two networks, okay, maybe this room, room and maybe another room, okay, we have two networks and we connect these two by a switch. But in an organization, so we may have a more complex switched or extended LAN or switched network, right? So in this case, we have 7 bridges, B1 through B7, all 7 switches. So as I said, you can replace bridge by switch, okay, so you don't need to worry about it, okay? So in that case, there would be a problem of what is called looping. Okay? So what is looping? To understand this problem, we take a simple case. Let's say we have LAN A and LAN B. So note that this is the notation of the thick line we use, the horizontal line represents a LAN. We use 2 bridges, B1 and B2. Now there's a loop. So loop here means cycle. There's a loop here. Right? So if we have a loop in a network, so there is a potential problem. So before that, why there should be a loop? Right? So why I need 2 bridges? Just one bridge should be okay, right? We can have either B1 or B2. We want to connect A and B, right? We don't want both A and B. But there are multiple reasons why, okay, we end up with this loop. One is to increase the reliability. That means if the switch becomes faulty or port becomes faulty or it's switched off or something, still, okay, A and B are connected by another switch or bridge, okay? So another reason is naturally the connectivity of the organization, okay, is something like this. So this is one office, maybe another office, so they all have their own switches, right? So naturally we want to connect, okay? So it becomes a complex network, something like this with some loops here. So some cycles are already formed, right? In addition to the reliability. So in this case, the potential problem is like this. Let's say there's a frame F received at LAN B. Let's say there is a frame F, we call it F. This is from our perspective, frame F. Assume that there's no entry for the destination at B1's forwarding table. That is, B1 does not know the destination address of frame F. So what it will do, it will broadcast it to the remaining ports, right? It will send it to the remaining ports. So in this case, this will be sent to LAN A, this port. Let's call this as frame 1. It's the same frame. Okay, just for understanding, I call it as frame 1. Okay, but it's the same frame but transmitted again. Is that okay? On the other port. Now let's say this is received by B2. B2 receives this frame. Assume that B2 also does not know the destination of this frame. It doesn't have an entry in the forwarding table. So what it will do, this frame F1, okay, will be broadcast to other ports. So it will send it to LAN B. So the same frame comes back. Let's say you call it as frame 2. Same frame is coming back to B1. B1 does not know that it's the same frame which it was sent, just coming back. Okay, even if it wants to know, compare the bits, just because all the bits are same, okay, it cannot conclude that it is the same frame, correct? Agreed or not? Just because the bits are same, you cannot say. So again, it considers the forwarding table. There's no entry for the destination. So it forwards it to the other ports. So let's call it as F3. Now B2 receives F3. It doesn't know the entry, so it goes back, puts back on the other line. So this will be looping forever until somebody learns, right? So this problem is not desirable, unnecessarily using up bandwidth, time, etc., right? So we want to avoid this looping problem, but loops should be there physically, but we want to avoid. So to avoid the looping, we want to create what is called spanning tree. So spanning tree, some of you might have studied as part of other courses, maybe particularly computer engineering students might have studied, computer science and engineering students, okay? So part of data structures or algorithms or other basic network course you might have studied. So what is a tree? Okay, what's a graph before that? Because this terminology is normally used, right, in the context of network. So if you assume these are all switches or routers, okay, so you can represent a network as a graph where the node, so this is a node in graph terminology, so this is an edge in the graph terminology. Nodes represent the switches are routers, okay. So they are connected by the links. And the edge represents the link which connects to switches, okay. So here you can see that there are multiple loops. There's one loop here, one loop here, one loop here, and there is another loop here, right? There's another big loop here. So there are multiple cycles or loops. Is that okay? So we do not want the frames. We don't want the loops because the frames will end up with looping inside some one or more cycles, okay? So we want to remove the loop to form what is called a tree. The tree here means it spans all the nodes. That means all 1, 2, 3, 4, 5, 6 nodes will be there in the tree. And some edges are removed. Some edges are removed from the original graph to make it a tree. Okay? A tree with n nodes, of course easy to prove, but I'm not interested in the theory, will have n minus 1 edges. So if you have 1, 2, 3, 4, 5, 6 nodes, you will have 1, 2, 3, 4, 5 edges. Okay? Now what is a tree? The tree is like a tree on the roadside. Right? If you take the tree on the roadside, there's no loop in the tree. Let's say somebody is sitting on the branch. Somebody is sitting on the, so there's a root in the tree, right? So you can see tree is something like this, right? So you have the branches. Okay? If somebody is sitting on this branch and he wants to reach another branch on the tree, maybe to pluck maybe some fruit or something, how many ways or how many paths or how many ways he can reach the other branch? Assuming that you are not allowed to jump, okay, you are not allowed to jump, okay, then you can easily notice that there is only one possible way, right, to reach from a branch to another branch on a tree, right? You cannot reach in multiple ways. Is that okay? So similarly, in a tree, the tree has some characteristics. One, it should be connected. That means you should not remove an edge so that it is disconnected. For example, you cannot, then one will be disconnected. Some part will be disconnected, right? It should be connected. So you should be able to reach from any node to any other node. So that is minimum required, right? And there should not be any loop. And there is a unique path from any node to any other node. So you take two nodes, there will be only one path. You take any two nodes, okay, there will be only one path, okay? And there is only one path from a node to the root. So here also this person, if he wants to reach the root, come down, okay? So there is only one path, okay, unless he jumps between branches and other things, okay? Is that clear? So one of the nodes usually is declared as a root. Assume that I call node 1 as the root, right? So there are multiple trees which you can create because, as I said, for n nodes, we can use n-1 edges to have a tree. So this is a because it satisfies all the properties. It's connected. Okay, there exists a path between unique path, only one path. Okay, between the root and the node, or between any two nodes. So this is also a tree spanning from this graph. So there are two spanning trees. This tree spans from the same graph. These two are. Okay. Now one of the trees, there may be more than one also. This tree we are calling as shortest path spanning tree. This is not a shortest path spanning tree. What is shortest path spanning tree? Shortest path spanning tree will preserve the shortest path from the root to every node. You take this node 1, let's say this is node 2, so this is node number 2. So from node 1 to 2, the shortest path on the original graph is this. Directly you can reach, which traverses only one hop, right? Of course, there exists another path, 1, this. Because there's a loop, you have multiple paths in the original graph. Here, the same shortest path exists here, right? But if you take this tree from 1 to 2, the shortest path is missing. Here it was the shortest path. Here it's a longer path. It uses a longer path, right? Similarly, other nodes. So say, for example, 1 to this, the same two nodes is there, but here 1, 2, 3. It has to traverse 3 links, right? So the tree which preserves the shortest paths, the tree which is formed by merging the shortest paths from the root, we call it a shortest path spanning tree. So we are going to look at the protocol which basically uses shortest path spanning tree for forwarding the frames. That means all the bridges, this can be connected. Physically, loops will be there. But when the frames are forwarded, they will be forwarded through only the edges in the tree. It means other ports. So this port, for example, so this port is there physically. Link is there, cable is there, port is there, but that will be declared inactive. They won't be used for forwarding. So how we are going to form the spanning tree? Okay? So, of course, if you might have studied spanning tree algorithms, I'm not going into the hardcore theoretical spanning tree algorithm and all. Okay? So practically a distributed spanning tree algorithm is used to form the tree. Okay? This tree is basically shortest path spanning tree. That means if you create a tree of shortest paths from a bridge to the root, okay, then you collectively you see that there's a spanning tree. Okay? And I'm going to explain the spanning tree protocol, the key principle. I'm not going into the full theory and other things with the help of this example. Okay? So here you can see that there are 7 bridges and a number of local area network lines, the vertical lines. And you can see that there are multiple loops. There is a loop here, there is a loop here, there is a loop here. Okay? And you can see that some lines are dotted lines. See, here. Some are dotted lines. Dotted lines means if you remove these links or you make this port inactive. Okay? Remove the links means physically it's not removed. Logically it is removed. Okay? So if you remove this, the loops will be broken. It will be a tree. For example, if you remove this dash line and this dash line, so this loop is broken. It's no longer a loop cycle. Similarly, if you remove this dotted line, this will be a This is a no loop portion of this, okay? Is that clear? So as an example, we are going to look at only this loop involving B1, B2, B3, B5, okay? So we are going to look at the protocol. It's a distributed protocol. Distributed protocol means multiple nodes are participating here. There's no central server or manager or node who keeps track of the complete information and choose the spanning tree. So everybody participates in that by exchanging some messages, okay? When messages are received, protocol means some messages will be received. When the messages are received, based on the information carried by the message, they do some action, okay? Then after some time, the protocol converges, the spanning tree is formed. When I say spanning tree is formed, so every every switch or bridge will know which ports are active, which ports should not be active. That means B3 should know that none of these two ports should be active. It just keeps quiet, that's all, correct? But note that it's physically connected, some frames will be receiving, but it won't forward anything, right? If it forwards, it will end up with a looping problem, that's the meaning. Right? So basically, we want to decide which links should be removed, which we should keep in the tree. That's the decision we need to make. And so for that purpose, every bridge okay, so this protocol is developed by Radia Perman. The standard is 802.1D. You need to know that there's a standard which every vendor or switch vendors they should follow when they manufacture these kind of switches. Okay? So each bridge has a unique ID. Some identifier is given. Say B1, B2, B3. Some identifier is given. Okay? But in practice, it may be a long identifier. But here, for example, I used 1, 2, 3, 4, 5. Okay? The bridge with the smallest identifier ID is chosen to be the root. The bridge with the smallest identifier will be the root. Because root has some additional functions also. It has to main, okay? Because it has to, okay, later I will tell, okay, what the root has to do. So it has to declare itself as the root periodically to make sure that, okay, everything is in place, okay? Then, we are going to create a tree of shortest paths, meaning that in that process, we will decide some ports are active, some ports are not active. And for each LAN, we are going to choose one bridge as the designated bridge, For example, you take A. This network A is connected to B3 and B5, okay? So between these two, only one will be selected as the designated bridge. That means for forwarding purpose, only the designated bridge will be forwarding it. The designated bridge who is closer to the root will be forwarding it because we are interested in the shortest spanning tree, okay? So in this case, if B1, B3 are at the same distance, but if you look at this B, let's say A, if A wants to forward through B5, it will reach B5, B1 in two hops, right? B5, B1, correct? But if it forwards through B3, B2, B1, it's a longer path, correct? So for A, the designated bridge will be B5. Similarly, you take C. For C, you can reach B1 through B2, B1 or B3, B5, B1, correct? There are two ways to reach. Because you have a loop, you can reach in multiple ways, okay? C, the frames from C can reach through B2, B1 or B5, B1, correct? But the one which is closer to the root is B2. So for C, the designated bridge will be B2. In that process, everybody will know, okay, the bridge will know, okay, I am the designated bridge for somebody, okay, I have to forward that frame. Okay, this port should be active, this port should not be active. Okay? So once the spanning tree is formed, the frames will be forwarded only along along the edges of the spanning tree, okay, because spanning tree doesn't have any loop. Okay? And each bridge forwards frames over each LAN for which it is the designated bridge. If it's not the designated bridge, okay, for somebody, it won't forward it. So these are all some key points to remember. Now the first question is, or the first step in the protocol is, the root should be chosen, the one who has the smallest identifier. Okay. Note that it's a distributed one, algorithm or protocol. Nobody knows that, okay, B1, okay, is active, alive, is powered on or connected to the network. B1 has the smallest identifier. That information is not known unless they send some messages, etc. So in the beginning, before spanning tree is formed, what is done is every switch or every bridge will declare. It's an election algorithm kind of thing. Everyone will declare that, okay, he is the bridge. Sorry, he is the root. B1 will say, I am the root. B2 will say, I am the root. B3 will say, I am the root, because they don't know whether there exists somebody else whose identifier is smaller than its own identifier, right? So what type of messages are sent? Those messages which are exchanged, okay, between the bridges, okay, we call them as configuration messages. It is of this form, y, d, x, y, d, x, where x is the sender, okay, x is the sender, y, what is y? Y is, okay, x believes y as the root. X believes that y is a root. So initially, it will be something like B3, 0, B3. That means B3 is the sender of this message, and B3 believes B3 is the root. So he believes himself is the root, okay? And the distance from X and Y is given as D. So when somebody self-declares, okay, I am the root, the distance from the node or bridge to itself is 0, correct? Then this kind of messages will be floating. Okay, when B3 is generating this message, somebody else may say, B2 may say, hi, I am the root, right? B1 may say, I am the root, right? So this configuration message will be received through multiple ports, and each bridge records the best configuration from that port. Let's say it has received a configuration message from the port. It learns, okay, what is the best message, okay, so far it has received. Okay, who is the root so far until this time. So initially, this message will be sent x, 0, x, because everybody believes, okay, that he or she is the bridge. Now, let me explain through this example. Okay, so we consider this particular loop. I'm not showing all possible configuration messages because there will be a lot of, because when B1 sends, B2 sends something, B3 sends something, B5 sends something. So I just show some very few messages which help to break the loop. Okay? I'm not showing other messages. Okay? Don't think that only these are the messages sent. There will be other messages sent. Even if other messages are sent, you can easily see that after some point of time, those messages will not be forwarded further because they are not the better configuration messages. So ultimately, they stabilize. Stabilize means, okay, they'll stop generating the configuration message. Everybody gives up, except B1, because B1 is the one who has the smallest ID. Only he has to win. He is the boss. All others will give up. Okay, there is somebody else, okay, whose identifier is less than me. Now, let's say B3 receives a message, B2, 0, B2. So this message is received from here on LAN C, right? So what B3 will do is, B3 will accept B2 as the root. So B2 is the sender, B2 believes B2 is the root, the distance is 0. Now B3 believes B2 is the root because 2 is smaller than 3. His identifier is 3, this fellow says his identifier is 2, right? So it accepts it. Then what it does is, that message, it tries to forward it to others. So it says, it prepares a new configuration message, B2, 1, B3. Okay. B2, 1, B3. It says B3 is the sender. Okay. It believes at this time B2 is the root. The distance from B3 to B2 is 1. That message will be sent here. Okay. Similarly, at that time, B1 might have generated a message, something like B1, 0, B1, right? So that message will be received by B2. on LAN E. So what B2 will do is, B2 has already sent a configuration message to other fellows, but now it has to change. It has received a better message, right? So B2 accepts B1 as the root, so it sends a new configuration message, B1, 1, comma B2. So B2 believes B1 is the root, 1 is the distance. And that information will be sent here on C. Similarly, this B1 message, will be sent to B5. B5 receives B1, 0, comma B1 on LAN D. Then B5 accepts B1 as the root, and it sends a message B1, 1, comma B5. This message, B1, 1, comma B5. Okay. So B3 receives this message here, B1, 1, comma B2. Earlier, B3 received this message, B2, 0, comma B2. So from the same B2 sender, it receives a better configuration message, B1. So now B1, this is a better configuration message, okay? So it accepts B1 as the root. It accepts B1 as the root. Okay? So B3 accepts B1 as the root because it's smaller than itself. And at the same time, it will stop forwarding to LAN C. Because for LAN C, okay, so far at this time, it has two LAN C, it receives from LAN C, so B3, B2 are attached, but B2 is closer to B1. B2 is closer to B1, so it will not forward through C. That means this line become dotted lines. Is that okay? Similarly, when B3 receives a message from B5, B1, comma 1, that is B5 believes B1 as the root, the distance is 1. So it is received from this on LAN A. So that means B3 and B5 are connected to the same LAN A, right? And B3 accepts this message, which is received from B5. So since B5 is closer to B1, then itself, it will stop forwarding this. This link will be cut. Okay? Is that okay? So now B3, both ports are removed. Both ports are removed. Note that, so in this case, it receives message from this port and this port. So through both of the ports, it sees that there's a better path. On A, B3 knows that B3 is closer to B1. So it gives up. Okay, on C, it knows that B2 is closer to B1, it gives up. But if there is another LAN here, something like this, there's another port, okay, then it will not give up. That means this may be the designated bridge for this. If this is the designated bridge for somebody, okay, there's no one else has a better route, then it will maintain the shortest path to the route. The shortest path for B3 is B2, B1. Okay. If it's not the designated bridge for a LAN, it won't forward it. Okay. So these two links are broken. Broken means they are declared not active. So here there's no loop. Similarly, you can also see that similar messages you can come up with and see that this is broken. B6 and B4. And note that for I, two bridges are connected, B6 and B4, and both are at the same distance to the root. Let's say I can reach B1 through B6 B1 or B4 B1, right? Both are at the same distance. If both are at the same distance, it breaks the tie in favor of the smaller ID. Use identifier to break is a tiebreaker. So that means that's why B4 is there, B5, B6 is removed. Because for I, B6, B4 are closer, but between B6 and B4, 4 has a smaller ID, so it chooses smaller one. Any doubt? Students, any doubt? So let's move on to the last part of this lecture notes, virtual LAN or VLAN. I think only from last semester I taught this. Sometime back I taught, then I removed, then I brought it back again, because VLAN you might come across here and there in the literature and practically also. So let's introduce what is this VLAN. Now let's look at maybe a simplified institutional network, okay, or some part of the institutional network. You have a router. Any network connected to a port of the router is a network, one network. It's one network. Okay? If you have another port, you have switches and other switches, there's another network, another LAN. So this is one LAN, of course, maybe like an extended LAN kind of thing. Okay. So this switch, okay, servers are connected to this, and below you find there are multiple switches connected to this. So one network or one subnet is this. I mean, later you will study the concept of subnet in part 2. Okay? So that is under port of one router. That's how you can understand. Right? If you have a network and under another port of the router, that is another subnet. Okay? A network, maybe let's say you take our network, split into multiple small subnets. Later you will study what is subnet, why it is advantages, etc. So same here, let's say that this, so for this part, okay, I use the book by Cross and Rose. Of course, maybe in his university, we have 3 departments, computer science, electrical engineering, computer engineering, okay. Of course, here we have 2 departments. Anyway, don't worry about it. So let's say this part of the network, these switches, they are located in computer science department, then electrical engineering, computer engineering department. Now, that there may be some need, okay, something like this. Let's say CS user wants to move his office to EE. The CS staff, okay. You can also see here, okay, sometimes our staff, electrical engineering, okay, they have offices in chemical engineering building, staff office, okay. Maybe at that time office is free, or maybe a bigger office room, or some reasons, okay. So CS staff has moved to EE office, but still he belongs to CS department. His office is moved, maybe office is in the next floor or something, okay. So, but he still wants to connect it to his office switch, CS department switch. These are the CS department switch. This is electrical engineering switch. So how it can be done? Next, broadcast domain. Broadcast domain means, I think we have already seen single broadcast domain, right? When a message is received, where they send, okay, wants to send it to all in the same network. There are many cases. See, for example, ARP, Address Resolution Protocol. I think I briefly mentioned in lecture notes 2, right? So every host attached to a network, okay, will know, they have maintained a table, ARP table or ARP cache, okay, which tells, okay, this is the MAC address or hardware address, this is the corresponding IP address. Okay, so that means if you treat all of them as a single network, single extended network, so all these hosts will know their own MAC address and MAC address of others in the same network, and also the IP addresses, right? So to know that, we need a protocol ARP, which has request and reply messages kind of thing. Okay, suppose this is the host, it does not know the MAC address of another IP address in the same network. How does it know it is in the same network? By looking at some bits in the IP address, destination IP address. It knows that, okay, this fellow is in the same network, but it has no entry for this particular host in the same network. So he will send ARP request message. Hi, I have this IP address. I want to know your hardware address. That will be broadcast to everybody in the same network. Note that the same network, within the same network. Okay? Is that okay? So it is a broadcast. Similarly, later you see DHCP, Dynamic Host Configuration Protocol, okay, to get the IP address initially when you boot up, when you join a network. So there's a protocol running, which also sends small packets as a broadcast packets or frames. Okay? Is that okay? So the broadcast here, it's a single broadcast domain. That means it has to be sent to all the hosts. So we may want to restrict the broadcast to maybe only computer science department or only electrical engineering and this. Maybe security reason or the efficiency reason why unnecessarily send this broadcast message to all the other hosts. Is that okay? So these are some advantages. To answer these questions, we have some advantages. Without VLAN also, we can have the connectivity. It doesn't matter. So what is done is VLAN is a switch. Let's say this switch has 16 ports. Okay, can be logically partitioned into 2 switches. So here you can see some ports are blue colored, some ports are yellow colored. Okay, so all the blue colored ports you can treat this as a separate VLAN switch, separate switch. Okay, and yellow color one is another switch. So this is something like there are 2 virtual switches. This is equivalent to, physically this is only one switch. Physically one switch, but this is as if we have 2 switches. One is the blue color with blue ports, the other one is yellow ports. Okay? So all the hosts, the computers which belong to this electrical engineering can be connected to the blue color ports, and color ones will be supporting the computer science computers. Okay? And they will be configured like this. Okay? They are configured to have multiple LANs. It can be more than 2 LANs also. Okay? So this is a port-based configuration. So port number 1 to 8 belong to electrical engineering. Port number 9 to 16 belong to computer engineering. Okay? So even if somebody moves, okay, we can configure the port such that it belongs to either electrical engineering or computer engineering. Right? The traffic would be isolated in the sense that the traffic from the ports 1 to 8, the blue ports, will reach only blue ports, any broadcast traffic or anything. And the broadcast traffic, okay, from 9 to 16 will be within that yellow ports only, because it's as if 2 different switches or LAN kind of thing. We can also define VLAN based on the MAC address. So here we define VLAN based on the port numbers. Instead, MAC address means the host they have their own MAC address, right? So based on the MAC address, we can also define. So if this MAC address is connected here, this belongs to electrical engineering. Okay, then tomorrow if you remove this host, you connect it to another port, automatically that becomes part of the computer science computer. If it is based on the MAC, if it is based on the port, okay, even if you remove one computer here, electrical engineering, okay, you connect it to another port, it depends on the port how it's configured. If that port is configured to electrical engineering, that is a electrical engineering, part of electrical engineering, that port, okay? But if it's MAC based, if it is based on the MAC address, so wherever you want to connect, that automatically changes to a new virtual switch based on the MAC address. It has pros and cons. I think you can think through it, or you can get from the book or the literature. What are the pros and cons of declaring or configuring based on the ports or based on the MAC address? Dynamic membership is there. You can see here, if you want to change this particular port, okay, from blue to yellow, that can be done. Okay. Forwarding, how we forward data from one LAN to another LAN, blue LAN to yellow LAN, how we forward data. We need a router to forward it, okay, from this LAN to this LAN, this virtual LAN to this virtual LAN. Is that okay? Otherwise, the traffic will go through only among themselves, 1 to 8 here, 9 to 16. We need a router, but that router, the purpose here is to forward only from this blue to yellow or yellow to blue. So usually, commercially, okay, the vendors will combine these two inside one single box, because it's not a very sophisticated routing function. This is a simple forwarding. So this router is inside actually. This is something like our wireless router at home, right? Okay, so it has both functions, wireless access point to connect, okay, wireless manner to the host, and also it does some routing function, IP address-based routing to connect to the internet, okay? So we don't have two different boxes. We put both of them together, though we call it as wireless router, it's actually router plus wireless access point, both together, okay? The next question is, there can be multiple physical switches, okay, where the VLANs can span. So for example, we can have one switch in this building, another switch in another building, okay, and some of the ports here are blue ports, some ports can be blue ports in the other building, okay. So some can be yellow here, some can be yellow here. Physically, multiple switches, and again within that we have VLANs. So in this case, how we connect these two? How do we forward traffic between this blue and yellow lines? So one of the ports will be declared usually as a trunk port. So this port and this port will be connected by a wire or cable. Okay? So this is used to carry the traffic between the VLANs. So within a VLAN or between these VLANs, when we say we don't use the standard Ethernet frame, in addition to that, we need to carry additional information like VLAN. This is a blue VLAN. Okay, this is a part of yellow VLAN. Okay, some additional fields are required. Okay, it's not just a normal Ethernet frames. Is that okay? So it's slightly modified. So 802.1q protocol is used. Okay, so it may add some additional information. Okay, so what are the additional information in the frame format? So this is the original Ethernet frame. You know that it's a 8-byte preamble. Okay, 7 byte sync, 1 byte start of the frame. This is the original one which we studied as part of Ethernet, I think, in the beginning. Okay, is that okay? It has destination address, source address. Then there is a field call which has two purpose, type and length. Then data followed by CRC. This is the original format. If you remember, if it is less than or equal to 1500, this means it's a length. If it is greater than 1500, this value is greater than 1500, it is used as a type. Correct? So two examples I was just mentioning. One is the VLAN. If it's a VLAN frame, this field value will be more than 1500. Similarly, if this frame is an ARP frame, let's say ARP request, ARP reply. So this is a special frame, control frame. It's not a data frame. The ARP frame also, the number which is carried in this field is greater than 1500. So these 2 bytes will be used to represent that this is a VLAN frame, 8100. It's obvious. If you find the decimal value, this is more than 1500. Okay, hex itself 8100. So it's more than 1500, right? So this is not a normal frame. So this number represents that this is a VLAN frame. So in this case, the next 2 bytes, so it uses extra bytes. Next 2 bytes will carry the VLAN information, VLAN ID, VLAN identifier. What is the identifier of the VLAN? So how many VLANs we can have? 2 raised to the power 12 VLANs we can have. Maybe under the single network. So 12-bit VLANs is a 2 byte and 3-bit priority field, a type of service. So if you want to prioritize, okay, this VLAN packets or frames have higher priority than this, that can be done. I think 1 bit is not used or reserved something. So next 2 bytes will be the length. Next 2 bytes will be the length. Somewhere you have to specify the length, how many bytes are carried in the payload, right? That means in the VLAN frame, we use additional 4 bytes. We use additional 4 bytes. Any doubt? Students, any doubt? So we are going to look at the next topic. This is wireless LAN. And mostly I follow book by Peterson and Davy, and few slides after slide number 26, I follow the book by Gross and Rose. Okay. So far we have studied, Ethernet, generally Ethernet, which is a dominant local area network. So basically it's a wired network. Okay. Similarly, we have wireless network. We choose wireless link for data transmission, right? So when you say wireless link, so a good example is Wi-Fi, right? This is what we are using, right? Okay. And wide area wireless network is the cellular mobile network, 4G, 5G. They are wide area wireless network, but we focus here on the local area wireless network, wireless LAN, Wi-Fi, particularly Wi-Fi. Yes. Wireless links transmit electromagnetic signals. So this could be radio signal or microwave signal, infrared signal. Okay, they have their own frequency range and other things. So if you are interested, you can refer the book and other things. Okay, why some signals are called radio signals? What is the characteristics? Microwave signals, infrared signals. Okay, so this could be short distance or long distance. Okay, to the cellular tower, or wireless transmission could be through satellite as well, maybe more expensive. Okay, through satellite, the communication through satellite. They are all wireless links. Okay. When you say wireless links, they all use the same medium, wireless medium. Okay. So when some host transmitted through the space, wireless medium, right? So the challenge is how we can share. It's basically, naturally, inherently it is a shared medium. It's a shared medium access, shared medium network. So we need a MAC, multiple access network. What happens if more than one try to transmit at the same time? That need to be addressed. Okay, so that is addressed by two approaches or two dimensions: frequency and space. Of course, when they transmit at multiple frequencies, this is one way. Okay, to avoid interference and other things. Okay, they can transmit at different frequencies. And the spatially they are separated. Spatially they are separated means the transmission here. So whatever we transmit, let's say it reaches only a few meters here. Maybe the same frequency can be used maybe another building spatially, because those do not interfere, right? And if you take any country, okay, so spectrum or frequencies, allocation should be done by some organization. Usually it be done by some organization under the control of the government. Is that okay? Because there are many applications of wireless radio, FM radio, AM radio, right? Maybe AM, FM, still we are using it, correct? Not much, but still we are using it. And you take cordless phone at home, that also uses wireless communication, okay? Bluetooth is there, Wi-Fi is there, right? And so when you say frequencies, even satellite TV also, right? So frequency, how the frequencies are shared, okay? And who allocates this? The government agencies will allocate. I think in US it's FCC, Federal Communication Commissions, and if I'm not wrong, in Singapore, IMDA, okay, does that allocation to service providers. The frequency allocations, spectrum allocations are done by IMDA, okay, which is a government organization. Specific frequency bands, starting from this frequency to this frequency, etc., they are allocated for specific uses. Some bands are reserved for military use or government use, because earlier the wireless communication devices were used for only by security people and police, okay? Military people and police, right? But nowadays, we are all using the wireless communication-based devices, the mobile phones and other things, okay? But still, some bands are reserved for the government use, okay? It could be may have their own network for privacy and other reasons, okay? Or confidentiality reason, or military purpose, or anything. Other bands are reserved for other purposes, public usage, AM, FM radio, as I said, for TV broadcast. Okay, the frequencies are allocated for this. Satellite communication, mobile phones, So they operate at certain frequencies. So when you buy, if you look at the specifications of your phone, you can see the frequency bands, which bands it operates, correct? And these bands, 3G, 4G, 2G, or 5G, should be allocated by the government to the individual carriers. Okay? Then there are some frequency bands which are license exempt, which can be used freely. We don't need to get licenses to use them. Okay? For example, Wi-Fi. We don't need any license to use Wi-Fi frequency. Okay? Certain frequencies are used for that purpose. Okay? It reaches maybe millions of people, and no need for getting license to manufacture a device. That frequencies, some frequencies, okay? Some frequencies are there, we don't need any license. But for cellular, mobile, and other things, there will be license, okay? But for Wi-Fi, no need for licensing. Similarly, the Bluetooth and other things. Okay? So some devices are exempt from license, the frequencies, but there are restrictions. It doesn't mean that there is no control at all. Anybody can do anything, okay? Why there are restrictions? You take, for example, cordless phone, so there will be a base at corner, the cordless phone you are talking. So there's a reachability limit, how long you can reach, correct? So maybe within a home here and the next floor you can reach, but you cannot just move away several hundreds of feet, still you can connect to the receiver, you cannot do it. Similarly, Wi-Fi also, correct? It has a limit. So whatever, so you should be close to the Wi-Fi access point, right? Maybe sometimes within the same house and different rooms, it may not be able to reach. Why we should restrict the reachability, the distance, the communication reach? That's the reason. Why? Because there are many people using it, license exempt. So the power which you are using should be limited, the transmission power. If you use more and more transmission power, then it means it can reach a longer distance, right? But there's a limit on the transmission power. Otherwise, there will be a lot of interference, okay, with the neighbors and other people. So they have a limit. That limit is enforced, right? And some techniques are recommended to be used. The spread spectrum techniques, of course, I'm not going into very details of those techniques, but some we will just touch upon, okay? So as the name says, is spread spectrum. Frequencies are spread to avoid or minimize the interference between multiple communications. Okay, so these are the restrictions which are used. Okay? So the idea is to minimize the impact of the interference. Otherwise, multiple peoples may not be used. Okay, so there will be a lot of interference. If you are allowed to manufacture a device or wireless router or says with very, very high power, right? You may be enjoying, but how about others? It may affect others, right? Okay? So for spread spectrum, there are two types, okay, from the beginning they are used. Of course, there are other techniques or variants developed. So we just look at the key principle. We are not going into the details of the communication details because we focus here on more network related topics. When you say frequency hopping technique, what is done is the signal, when the signals are transmitted, it hops through a random sequence of frequencies. It doesn't transmit one frequency. It transmits through multiple frequencies. First transmits F1, then F2, F3, F4. So it hops through multiple frequencies. And which frequencies, okay, the sequence of the frequencies is random. That only the sender and receiver will know. Sender and receiver will know. They will be locked. They know the sequence of frequencies. Okay, which sequence it has to send, which sequence it will be receiving. Both of them will be using the same algorithm. When you say random, usually it is a pseudo-random, okay, because after some time that random will repeat the patterns. But anyway, let's not go into the details. Assume that they are random sequences. So this is frequency hopping method. There's another method, direct sequence method. The direct sequence method, each bit is going to be replaced by multiple bits, and accordingly, the frequencies, okay, will be spread or become wider. Okay, so maybe I explain this with an example. Okay, for each bit which you want to transmit, it's replaced by a group of bits, and this, how it's going to be replaced, it's based on a random sequence. Assume that this is the data stream. This is the data stream, and here in this case, we are using, let's say, 4-bit chipping code, in the sense that for each bit, let's say this is 1, 0, 1, 0. Instead of sending 1 bit, we are going to send 4 bits. That 4 bits depends on a random sequence, which is known to sender and receiver. Both these know. Okay, this is the sequence being used. Okay. So this random sequence is given here: 0, 1, 0, 0, and 1, 0, 1, 1. So what is done is, this 1 now is stretched into 4 ones. It's stretched, meaning that this will be exclusive OR with this. 1 exclusive OR 0 is 1, 1 exclusive OR 1 is 0, 1 exclusive OR 0 is 1, 1 exclusive OR 0 is 1. Next, this 0, next 0 is stretched into 4 zeros, and the corresponding next, it will be exclusive OR with the corresponding 4 bits in the random sequence. 0 exclusive OR 1 is 1, 0 exclusive OR 1, 0 is 0, then 1, 1. Okay, so instead of sending this, we will be sending this. So the signal is sent across a frequency band which is n times wider, 4 times wider here. Of course, there's a theory, okay, why it works correctly or why minimize interference, this, that. So let's not go into those details. So when we say wireless technology, okay, there are 2 key parameters which, okay, we need to address, are associated with each wireless technology. We have bandwidth or data rate and the communication reach. What's the data rate? You take Bluetooth, okay? You take, for example, Wi-Fi or 3G, 4G, 5G. Okay, first question is, what's the data rate? Okay, what's this? Is 100, can I send at rate 100 Mbps, 50 Mbps, 20 Mbps? Okay, the data rate. Each technology comes with its own data rate. Then the communication reach. How long the signal can reach? How long the signal can reach? Okay. See, for example, you take Bluetooth. The standard is 802.15.1. Okay. The data rate is usually small, few Mbps, and the distance is also usually small, 10 meters. Okay, because what purpose you use Bluetooth? Can you give example where you use Bluetooth? Yes? Yes? Earphone. Okay, there's a dominant one nowadays, right? So you want to play a song, okay, or you don't want to listen to the lecture, you want to listen to your song, you can do that, okay? So how far the distance, right? The few meters should be okay, correct? So we don't need very long distance between the device and your Bluetooth and the mobile device or this, right? So 2 Mbps is okay, because Bluetooth, you want to just hear, you are not watching it or anything, so it's just a music, okay? So few Mbps should be fine, okay? Wi-Fi, we want high data rate because we want to browse the internet. The applications are different, okay? So nowadays, few hundred Mbps or Gbps, okay, they're also coming up, right? The new evolutions. And ideally, 100 meters, but doesn't happen, okay? 100 meters means, but even within a small house, sometimes it doesn't work, right? It's also good business, okay? But maybe because of the walls and other things, right? If the signal goes through multiple walls, even though they are very close, but it crosses two walls. One wall is okay. Two walls, when it crosses, it loses its strength, right? Okay, so you need to place the Wi-Fi router at an appropriate place. The location is very important, right? Otherwise, you should have wireless extender and other things. But ideally, 100 meters, but this is the maximum, worst case, under conditions apply here, okay? And 3G cellular, until a few years ago, we were using 3G services. So that time they were very popular, okay? So they could support few Mbps, tens of kilometers usually, because cellular mobile means you want to connect to the remote cellular tower. It's not like Wi-Fi access point at home or at the university where there are many access points, okay? Similarly, 4G, that rates improving, okay, claim to have few hundred Mbps. I don't give the exact numbers. Similarly, 5G, 6G, people are talking about it. So the data rate would be higher, right? But how the wireless devices are connected? So actually, there are two types, but the one which is the popular one is the infrastructure-based one. Okay, so usually the endpoints are different. That means the devices do not communicate directly. Let's say you want to send something to another person, we don't directly communicate to it. Usually, the wireless devices are connected to a base station or the access points. Okay, so at home we have wireless access point, right? Universities also wireless access points are there. So if it's a 4G network, the cellular tower, the cellular mobile tower is the base station or access point, right? So endpoints are different means on one side we have the host, the other side we have the fixed base stations. Usually they are not mobile, okay, fixed. Okay, at the back end they are all connected by a wired network. So this we call it as infrastructure-based wireless network. We need an infrastructure. We need access point. We need some network at the back end of the access points to connect to the internet. Okay, we need cellular tower, okay, which is connected to switches or router at the back end. Okay, it's infrastructure-based. Of course, we have wireless mesh network or ad hoc network. There is no need for infrastructure. There is no tower or there is no access point. Maybe, let's say, inside the forest or mountain area, okay, where if we cannot install infrastructure, okay, this might have been the case in the beginning, okay, a few years ago. So if for some reasons cost is an or other hurdles, we cannot infrastructure, then in that case, these wireless networks can work in ad hoc mode. Ad hoc mode means everybody is a peer, all are equal. So a wireless host can directly communicate to the another wireless host. Of course, there should be a protocol running to support it. Okay? So in this case, this mobile node can reach here and here. So if this mobile node wants to reach this, then it has to go through this. Okay? So the protocol should support it, the mobility. Mostly it was developed for the military purpose, okay, which do not have access to the infrastructure. But we are not studying this wireless ad hoc or mesh network. So what we look at is the infrastructure-based or access point-based wireless LAN. Okay? In terms of mobility, in wireless network means usually we want mobility, right? But wireless and mobility are different. Mobility means we can move. Wireless means the communication is wireless, right? Wireless doesn't mean mobility automatically, right? So there are different levels of mobility. No mobility. In some cases, the communication is wireless, but it's not mobile. Okay? Example is WiMAX. So maybe a few years ago, it was becoming popular, but I don't think, okay, maybe it has lost its popularity, okay, now. So the key idea here is that there will be the receivers or antennas, whatever it is, maybe installed maybe on the buildings. They are not mobile. They are not mobile, but they can still communicate. They can communicate. The Bluetooth. Bluetooth supports mobility, okay, of the device. But the mobility is within the range of the base station, right? You have the earpiece and headphone or whatever it is, you have the mobile device. So there is a there is a range within that you can move. You cannot move away from there. But if you take 3G for cellular mobile network, 4G, 5G, mobility between bases is supported. Okay, let's say you are traveling in the train or car. You don't know. Okay, initially you may be attached to one mobile, the cellular tower. After some time, your device may be attached to another tower. That is the mobility between the base stations are supported. Even Wi-Fi also, of course at home usually we have one access point, but like organizations like universities and big companies and all, nowadays many access points are there. So your device can be connected to Wi-Fi even when you move from one place to another place. You want a seamless connectivity. Okay, so you can move from one access point to another access point. So without the users knowing, your device would be connected or handed over to another access point. But Bluetooth, it won't happen. You cannot move from one to another. Okay, so you should move all together, both the devices, the earpiece and the phone together, okay, within the range. So particularly, we are going to look at 802.11, this Wi-Fi. I think I mentioned earlier, it's not known why it is called Wi-Fi. Okay, some says wireless fidelity, some says like Hi-Fi. Okay, some name Wi-Fi is given. Anyway, let's not worry about it, why it is called Wi-Fi, okay, but it's quite popular, right? Become part of our life, Wi-Fi, right? So it's used for the purpose of the local area network, so inside home or offices, etc. Something like the initial Ethernet or token ring or whatever it is. But the problem here is the medium access control, because there are many who are using the same medium, they are using the same access point medium, so how the access can be controlled. Okay, so we are going to look at MAC used in the Wi-Fi. Of course, it has some more functions when compared to Ethernet network, like security. So wireless usually come with WAP and other security mechanism. We are not going into that. Similarly, power management, you can have auto sleep and other things to save power, because wireless device means usually the power management is important. We are more concerned about the power and energy, right, compared to the wired network. So let's look at the evolution of the wireless standards. So because if you buy a device, your phone, or let's say laptop or anything, okay, so usually we will see the numbers like 802.1B/G/N/AC, something like this, right? Have you seen this? B, G, N, AC. What's the recent one? Have you seen anything beyond AC? Yes? AX, Wi-Fi 6, AX? AX? Okay. Anyway, I'm not including it in the notes. So let's see B, G, N, AC, okay? So that evolved from B, G, then N, okay? These are different variants, okay? AC. You don't need to memorize, okay? But as a network engineer, you should know how they evolved, what is the difference, okay, between these. So the original one, okay, when it was developed, 802.11, so there are two physical layer standards. Layer 1, physical layer transmissions and other things, which is not our focus, but I think I briefly mentioned the key principle. One is frequency hopping. So it hops through 79 different frequency bands. Each frequency band is 1 megahertz width. 79 frequency different bands are used. Then direct sequence, it uses 11-bit chipping sequence. The example which we looked at is 4-bit. 11-bit means each bit is replaced by 11 bits depending on the random sequence. Yeah. Both standards were using 2.4 gigahertz. Even now, you can see any wireless device, right? 2.4 gigahertz, and there is another band, 5 gigahertz. Okay, so if you take mobile phone, for example, the high-end devices, okay, more expensive devices, right? They support both 2.4 gigahertz and 5 gigahertz, correct? Even our NUS network also supports both 2.4 and 5 gigahertz. 5 gigahertz band, if it operates on 5 gigahertz, usually the data rate is higher, but the reach may be shorter when compared to 2.4 gigahertz. 2.4 gigahertz, even at home also. So it depends. Okay. So if you want high data rate, you choose the 5 gigahertz version instead of 4.4 gigahertz version. So it started with 2.4 gigahertz band, and initially the data rate was maximum 2 Mbps. But people were happy. Okay. First time the wireless connectivity was evolving. Even in 2Ks, okay, they were not initial 2Ks. No, it was not so popular. Right? It was just slowly evolving. Only recently, maybe in the recent decade, became very popular. Okay. Then developed 802.11b. Before A, B was developed. Okay. It uses a variant of direct sequence. The data rate is 11 Mbps. It was seen as a huge improvement, 11 Mbps. Again, it uses the 2.4 gigahertz. Please note that these bands are license exempt. Okay, when there's a restriction on power and other things, but for using it, nobody should pay to the government to use the frequencies. Then came 802.11a, not popularly used, okay, because there are other improvements. It supports or provides up to 54 Mbps, but it uses orthogonal FDM. Again, just our knowledge sake, we are not going into the details. But it runs on 5 gigahertz band. Then developed was 802.11g. It's backward compatible. That means whatever has been developed for 11b, that works with G as well. Okay, it should usually when it evolves, it will be backward compatible. Okay, the previous version also it will support. That's why they say BG///N, etc. So it uses 2.4 gigahertz, but the data rate is as high as A, that is 54 Mbps. Then evolved N, improvement of G, same 2.4 gigahertz, but it could provide data rate of few hundred Mbps. That is N. Then AC. Okay, N uses a new technique, MIMO, multiple input, multiple output antennas. Again, we are not studying those things as part of this course. AC runs on 5 gigahertz, not on 4 gigahertz, sorry, 2.4, it runs on 5 gigahertz. It's an improvement on this, and it can even support in the order of gigabits per second. So this is how the wireless standards have been evolving. So now we are going to look at the MAC used in Wi-Fi. Okay. It uses CSMA-CA, different from the Ethernet. Ethernet uses CD, right? Collision detection. But it does not use collision detection. Okay, there are some reasons why it doesn't use CD, something similar to Ethernet. Okay? Because if you look at the Ethernet, the connectivity is wired connectivity, right? If there is a collision, some jam signal is sent, okay, and it has sufficient energy, okay, it drives sufficient energy so that the sender will know that there is a collision. But in the case of wireless transmission, the connectivity or the link connectivity is through wireless medium. Usually the signals will become weak quickly due to fading and other effects. So wired communication, the attenuation is low. Wireless, quickly they fade, the signals are fading, it becomes very weak. So implementing collision detection is not a good idea. It's not a good idea, okay? And also later we see cases of what is called hidden node problem, etc. So some cases may not be able to detect the collision. So better don't use collision detection mechanism. Instead, it's going to use CA, collision avoidance. So it will make sure that collisions are avoided. It doesn't happen. Okay? CS, as you know, carrier sense. That means every device should be able to tell whether there is any ongoing transmission or not. It can sense the ongoing transmissions. Why? It should be there. Why? Because if it senses that some transmission is going on, there's no point in trying a new frame transmission, right? So it can try only when there is no ongoing transmission. So for that purpose, CS capability is that carrier sense. So now we are going to look at two key characteristics which are observed in wireless. One is hidden node problem, the other one is exposed node problem. Okay. So now look at this. There are three, this I tried to explain with examples, easy and quickly grasp these things. A, B, C are the three wireless nodes. Okay. And this circle, A, I show circle for A and C with the center. A is at the center of one circle, C is the center of one circle. That means this shows the reachability of A. That is when A transmits a signal, how far it can reach. So this is this circle it can reach. Similarly for C, it can reach any device which is within this circle. Right? That means A's transmission can reach B. C's transmission can reach B. Is that okay? Because B is within A's circle, C is within B's, B is within C circle as well as A circle. Okay? So here this example, we assume that the signals can reach just the nodes to its left and right. That means B can reach A can reach B. C can reach A, B can reach A. So A to C directly not possible. A to C is not possible. They are hidden from each other. They are hidden from each other. Because A's transmission cannot reach C, C's transmission cannot reach A. Now let's say A sends to B. Let's say A sends to B, sends a frame to B. Okay. So when this transmission happens, because A's transmission cannot reach C, C does not know about this transmission because whatever A sends cannot reach C. Whatever A sends cannot reach C. So when C senses the carrier, it thinks that the medium is free. The medium is free. It's not receiving anything. Correct? So if A sends to B, C thinks it is free. Let's say C also sends a frame to B. When C sends to B, that frame cannot reach A. C cannot reach A. So when C sends a frame, that transmission cannot reach A because A and C are hidden from each other. They are very far. So what happens? A also sends to B because A thinks there is no ongoing transmission. C thinks there is no ongoing transmission. So C also sends to B. But there is a collision at B. Why there's a collision at B? B receives two signals now. B receives two signals at the same time, so there is a collision at B. So there's a hidden node problem. So we saw the protocol should address this, should take care of this kind of situations. Is that okay? So if it is Ethernet, we cannot say that A and C are hidden because they are all connected by a wired link, so they can communicate. There's no way. Okay, the signals will reach. Whatever A sends will be reached by, it will reach C. And C's signals will reach A in Ethernet, but here it cannot. So what is this problem? Although A and C are hidden from each other, their signals can collide at B. A and C, they think they can transmit, but somewhere their signals are colliding. The other one is exposed node problem. This is slightly different problem. or maybe it's a good feature, okay? See, now you consider A, B, C, D. We have shown the circle for B and C. We have shown circle for B and C. Assume that everybody can reach to the immediate left and immediate right. Okay, we are not showing other circles. Okay, so the reachability is such that A can reach B, B can reach A, but A cannot reach C, B cannot reach D. B and C, they can reach each other. C and D can reach each other. Okay, so maybe let me put as a bigger figure. So in that case, let's say B sends some data to A, some frames to A. B sends frame to A. So when B sends to A, how about C? Will it receive it or not? When B sends a frame to A, whoever is in B circle, the blue circle will receive it, correct? So our idea is any nodes on the left and the right will receive it in this example. So when B sends to A, C will receive it. So now the question is, because C is receiving, should C keep quiet? That means, can it transmit or not? Okay. So let's say it wants to transmit to D. It wants to transmit to D. Can it transmit? So in this case, it can transmit it. That should not be a problem. That should not be a problem because whatever C sends will be received by D. Whatever C sends will not be received by A. So A receives only from B. D receives only from C. There are no simultaneous transmissions received at a node. So there's no collision. You note that collision occurs at the node when it receives two signals. So A will receive only from A. A receives only from B. D receives only from C. These two transmissions can happen simultaneously because A and D are far apart. Okay? So the problem is this. Although B and C are exposed to each other, that is whatever B sends will be received by C, whatever C sends will be received by B. Okay? In terms of transmissions, okay, if B transmits to A, that transmission will not interfere with C transmits to D. This is an exposed node problem, okay? In fact, we should not call it as a problem. It's a good feature, actually, okay? We can have multiple simultaneous transmissions. So how it is addressed by collision detection algorithm. I take a few more minutes to complete this, maybe 1 or 2 slides, then we stop, okay? So let's quickly look at the key idea, okay? The idea how to avoid the collision. So the algorithm is called MECA, multiple access with collision avoidance, MECA. So the key idea here is that because it wants to avoid the collision, there should be a coordination. Somehow we need to decide who wants to send, who wants to receive. That information should be exchanged. In Ethernet, there is no coordination at all. So in this case, the sender sends an RTS frame first. Whenever it wants to send, it sends RTS frame, request to send to the receiver. And this RTS frame will also include a field in the header. It says how long it wants to hold, how long it wants to send, maybe in terms of microseconds or something, how long it wants to send. Okay? So that also tells the length of the data frame. Now the receiver, if it's ready to receive, it will reply with CTS, clear to send. Okay, you can send it. And it will also echo it. Okay, you wanted to send for X microseconds. Okay, you can send it for X microseconds. So they are done. Once a sender sends RTS and it gets CTS back, it's ready to send. It can send it. Okay? Now, very simple protocol. Now we will see how with this RTS and CTS, okay, it helps to address these two, the hidden node problem and exposed node problem. Okay? So if you look at the hidden node problem, you take the hidden node problem, okay? So what was the problem, if you can quickly recall? A wants to send to B, C also wants to send to B, correct? A sends to B. Because A transmission does not reach C, C thinks it is free, medium is free, so C also sends to B, sends the collision at B, right? How it is resolved? So A sends to B means A sends RTS. A sends frame RTS, request to send to B. Now B responds with CTS. But since B and C, they can reach each other, correct? The CTS will also be received by C. Note that C will not receive RTS. C will not receive RTS because this signal cannot reach C. So C thinks medium is free. But it receives CTS. When it receives CTS, it understands that there is a node who is close by, within its reach, who is receiving or who is going to receive some data. That means if C tries to send any frame, that frame will collide at this B. It can, because by just receiving CTS, will know that somebody is close to him who is going to receive data, correct? So it should avoid transmit any data. If it transmits, then definitely it will collide with that receiver, whoever it is, B or whoever it is. Very simple. So this problem is addressed. So that's what it says. Any node who sees CTS know that it's close to the receiver, so it will not transmit certain time. How long it will not transmit? Because CTS tells when it sends clear to send high, you can send it for X microseconds. So until that time, it will just keep quiet. Then after the time is over, it will see whether medium is still free. Then it can try with RTS. Now, how the expose node problem is addressed? So in this case, we said B can send to A, C can send to D. Both can happen. How it is done is, when B wants to send to A, so it sends RTS, and that RTS will be received by C as well, right? So because B is within the reach of C, so whatever B sends, C also, so C is receiving RTS here. But A responds with CTS to B, but this CTS will not receive C. This CTS will not receive C. Okay? Because if you draw A circle here, A circle will be something like this. A as a center. Okay? So that's why I said any node can communicate to the next node on the right side and on the left side. So A can reach B, B can reach A cannot reach C. That is the assumption here. So when it responds with CTS, that will not be received by C. Now C has received RTS, then it will wait for some time whether it receives CTS. If it does not receive CTS, that means it understands that the receiver, whoever it is, who is going to receive, is very far. Receiver is very far, so it will transmit. It can transmit an RTS to D. So this RTS to D will be received by B. Doesn't matter. But when D receives a CTS, this D CTS will not receive B. It will not reach B. Because according to the reachability, D can reach C, but D cannot reach B. Is that okay? So these two transmissions do not interfere. It can happen simultaneously. So that's what is said here. Any node that sees RTS but does not see CTS That means it's not close to the receiver to interfere. So it's free to transmit. Is that fine? In the last slide today, collision avoidance with an acknowledgement. Okay, MECA, there is no separate acknowledgement, but there's other protocol which is used, MECA W, MECA for wireless LAN. Okay, so it does not explicitly say acknowledgement. Actually, it uses acknowledgement. So in that case, the receiver sends an acknowledgement once it is done. That is, initially RTS, CTS are exchanged. Once it receives the frame, it sends an acknowledgement back to the sender. Note that in Ethernet there is no acknowledgement. Okay, so here there is an acknowledgement. That means in the previous cases, if anybody has seen CTS, that means the receiver is close by. CTS means then it will wait for the acknowledgement. So when it receives acknowledgement, that means the ongoing transmission is done. That's what it means. Okay, but now here still there is a problem of collision with respect to the control frames, not data frames, RTS frames. So let's say two nodes find the medium free. Let's say two nodes at the same time send RTS. Maybe you look at this problem. So A wants to send to B, C wants to send to B. So here we assume that first A sends to RTS, B responds with CTS. So B, the CTS frame, CTS control frame is received by C. So C knows that it should not send it, right? But it may so happen that that's also possible, that A and C, they find medium free. At the same time, they are sending RTS. So A to B, C to B. They can send RTS at the same time. So in that case, both will collide at B because B is receiving multiple signals. Note that there is no collision detection mechanism. There is no collision. B is not detecting the collision, but A and C will know about collision because in that case they will not respond CTS. They will not receive CTS back. Because RTS has collided, B does not know that it has received RTS, correct? It's not a valid RTS received. So B will not respond with anything. It doesn't detect collision, but it doesn't respond. Because there is no CTS received by C, they know that their RTS frames are collided. So they will use binary backup, something similar to Ethernet. First, they toss the coin. Okay, they decide whether it has to get 0 or 1. Based on that, they defer. Okay, they defer for 0 slot or 1 slot. Next time also, its RTS collides consecutively. Then it will generate 0 to 3, then 0 to 7, something similar to Ethernet. Note that that collision happens for the control frames, not for the data frames. Okay. Okay, let me stop here. Still, some more slides are there. Maybe I try my best to complete it on Wednesday after the tutorial. Okay, if still not left out, then I may have to cover this when I conduct a special contact session. Okay, before the test. As I said, I will be arranging a Zoom session before the test to go through the sample questions. And to clarify doubts if any. In case I cannot complete the remaining slides, they won't take much time, okay, on Wednesday class after the tutorial. Okay, I will do it before the test, don't worry. And this lecture note is not included for the quiz. For the quiz, it's lecture notes 1 to 5. But for the final exam, you will have everything, 1 to 6.